Assalamualaikum and hi, my name is Nushaira Mituzupati. I'm from Group 2. I want to present about introduction of determinant. Determinant is a distinct numerical value that is computed from a matrix, and it is highly helpful when analyzing and solving problems of system linear equation. And it has wide application in engineering, science, economic, and social science. Determinant of the square matrix denoted by a number, real or complex, where A equal to ij with element of A. Determinants are essential tools that provide a distinct viewpoint and deepen our comprehension of mathematical phenomena, whether analyzing complicated equations, investigating the complexities of linear systems, or diving into geometric computation. Now I will continue with characteristics of determinant. First, there are switching rows or columns. The determinant remains unchanged when rows or columns are switched. Second, change in sign upon switching two rows or columns. The sign of determinant flips when any two rows or columns are interchanged. And third, zero determinant for duplicate rows or columns. Determinant becomes zero if any two rows or columns are identical. Next, expression as the sum of determinant. A determinant can be expressed as the sum of two or more determinants if elements in a row or column are represented as the sum of two or more terms. And last, invariant under equimultiples. The determinant values remain constant if equimultiples of elements in other rows or columns are applied to each element of any row or column.
Hi, salam sejahtera. I'm Ivan and I like Clinton. Today I'm going to talk about using determinant in real life application domain. So first is solve electric circuit problem using determinants. This is the sample circuit that we can use determinant to solve the problem in the electric circuit. Okay, first based on the figure 1 we can get equation Kirchhoff law voltage law for loop containing R1, R2, R3 and V1. So we can get first equation. Second, Kirchhoff law, voltage law, the loop containing R4, R5, V1 and V2. We can get the second equation. And third is we can get the third equation. Using this equation, we can get the matrix. Using this matrix, we can calculate the determinant of this matrix. After that, we can use the Cramer's rule to get the answer. First of all, replace the first column with this V1 over R1 0 0. Calculate the determinant and divide by determinant to get determinant that we get from here. After that, we can get the high one value. Second is we can get high two by replacing this. After that, we can calculate the determinant, and third also same like that. After that, the second application is determinant in computer graphic and 3D image processing. The information matrices in computer graphics, we represent 3D objects and image as collection of points in space. To manipulate these objects, we use matrix to perform transformation like rotation, scaling, and translation. Transformation matrix in computer graphics, we represent 3D object and image as collection of points in space. To manipulate this object, we use matrices to perform transformation like rotations, scaling, And translation. Zero determinant reflects that a determinant of suggests a volume collapsing transformation, often indicating flipping, mirroring, or projecting onto a lower dimensional space. This can lead to unnatural looking or distorted result. Using this determinant, we can get the computer graphic and 3D image processing. Specific formula for this rotation matrix: rotation around the x-axis, rotation around y-axis, and rotation around the z-axis. Example of works: 3D modeling and animation. Rotating a character's arm in 3D animation, spinning a 3D model of car in a virtual showroom, painting entirely a 3D scene in video game. Image processing, applying perspective correction to architectural photos, correcting lens distortions in wide angle images, reconstructing 3D object from multiple 2D views. So these are the example of the calculation. Rotating in cube in 3D, we have simple cube represented by 4 vertical in 3D space. So A, B, C, D, A, B, C, D. Step 1, define the rotation matrix. The rotation matrix for 30 degrees around the x-axis is, okay, we can get this, where cos 30 degrees we can get 0.866, and 6 sine 30 degree we can get 0.5. Step 2, apply matrix multiplication to each vertex. Multiply each vertex represented as 1 times 3 matrix by rotational matrix. We can get this. Similar to perform multiplication for B, C, and D. Step 3, analyze the result. After multiplying all vertices by Rx, we have 4 new vertices representing the rotated cube. The crucial point is that the determinant of Rx is cos 30 degrees cos 30 degree times cos 30 minus cos 30 times equals to 1. This tells us the volume of the cube remain unchanged after the rotation. Thank you.
Hello, a very good day to doctor and everyone. Myself Mukesh Periyasamy, number metric CI230048. Now I will like to explain about the using determinant in real life domain. First, I will discuss about the concept of 2D rotation in computer graphic by using determinants. Okay, let's start by understanding what 2D rotation entails. In computer graphics, 2D rotation involves altering the orientation of object or a coordinate system within a two-dimension plane. The primary goal is to change the direction of graphical component around a specific point or a axis. Before delving into the details, it's crucial to grasp two fundamental components of 2D rotation: the rotation angle theta and the rotation center Cx and Cy. The rotation angle determines the degree of rotation, measured in radians, while the rotation center denotes the point around which the rotate occurs. Let's move into the trigonometry functions. How trigonometry functions play a role in representing 2D rotation. We use functions like cosines and sines to describe the original coordinates of P, A and B, which can seen in the image above. As well, they are transform counterparts P, A and B. Okay, for the matrix representation, we can express 2D equation in matrix form. The equation was A equals to x cos theta minus y sin theta, and the B was x sin theta plus y cos theta. Can represent as a matrix multiplication of the original point matrix with the rotation matrix, which can seen here. Okay, for the rotation matrix, let's look closer at the rotation matrix. R, it's defined as cos theta, sin theta, negative sin theta, and cos theta. This metric facilitates the rotation process, allowing us to perform both positive and negative rotation by manipulating the value of the angle theta. Okay, for the conclusion, understanding 2D rotation in computer graphics is essential for manipulating graphical element efficiently. By grasping concepts like rotation angles, rotation centers, and metric representation, we efficiently rotate objects in a 2D space to achieve desired visual effects. Okay, now I will move to my second topic, which is diving deeper into determinant and structure stability. Okay, let's understand the significance of determinant in analyzing the stability of complex structure like bridges, building, and trusses. Determinants serve as a powerful tool behind the scenes, enabling us to access the structural integrity of various constructions. To comprehend structural stability, we need to understand structural stability. We must grasp how to external forces such as wind, traffic, and weight impact structures, leading to deformation of or displacement, solving a system of linear equations that represent a equilibrium of force, and the displacement is essential for analyzing structure stability accurately. Okay, let's move to the importance of determinants. Determinants play a pivotal role in determining whether equations have a unique solution, which is crucial for accessing structure stability. A non-zero determinant indicates a unique solution, ensuring predictable deformation under applied loads. Conversely, a zero determinant suffers a potentially instability or structure failure. Okay, this is an example. Let's consider a practical example of analyzing a simple truss. In figure 2, we have a truss bridge with the label nodes and forces. To analyze its stability, we follow a systematic process, beginning with defining element and properties. Okay. Stiffness metric calculation. Now let's dive into the calculation. We perform the stiffness metric based on the trusses geometric and Young models. The stiffness metric is a fundamental component in accessing the structural stability of the trusses. Okay, we can know that the zero determinant of the stiffness matrix K was the 62,500. It indicates the stability for truss under a given loading condition. This example underscores the importance of determinant in ensuring structural integrity and safety in engineer design. Okay, this was a very simple example. In the real life application, it's important to note the real world structure analysis involves a more indicates calculation, considering factors such as support reaction, multiple load cases, and various type of elements. Understanding determinants and their practical application is essential for engineering professionals. That's all from me. Very thank you for everyone.
Hi, Assalamualaikum. My name is Niza Atira Shamimi from Group 2. We will explain about application of determinant based on geometry and Young modulus. So as you can see here, this is our code that we have been programmed. This C program allow the user to input a 3x3 metric representing the stiffness metric based on the geometry and Young modulus. And then it calculate and display the determinant of the metric. The determinant is a mathematical operation that can be applied to square matrices and has various applications, one of which is in solving system of linear equation. So you can see here there is a header file include studio.hash, a function declaration, void metric, main function calls the metric function, that return 0 to indicate successful program execution. A metric function that prompt the user to input the number of rows and columns. Allocate memory for a 3x3 matrix using dynamic memory allocation. Ask the user to input the element of the stiffness metric. Display the enter metric calls the calculate determinant function to compute and display the determinant. And then there is also calculate determinant function, and then all the stuff that we need to make our coding a success. Overall, this program demonstrates the application of determinant in the context of a 3x3 stiffness metric, which is relevant in the field of material science, particularly in understanding the behavior of material under stress and strain based on Young modulus. Next slide is the output of the program. So this is the output of the program of the code. So first, user insert the number of the metric and the program will show the metric in their coordination. Later, the program will calculate the determinant of the metric. Next, this is the manual calculation. As you can see, our manual calculation for determinant is the same answer as the program that we've been code. So that's all from me. Thank you.
In conclusion, determinants demonstrate their value in resolving intricate issues by serving as essential instruments in a variety of sectors. Determinants solve for real-life applications that have been stated, which are electric circuit problem, computer graphics and 3D image processing, 2D rotation in computer graphics, and structural stability. To be more specific, firstly, determinant helps to provide a methodical and quantitative approach, whether they are used in engineering to determine structural stability or in computer graphics to facilitate 2D rotations, or in electric circuit analysis utilizing Cramer's rule. Determinants also help to calculate unknown currents and voltages precisely in electric circuits, and they guarantee perfect rotations in computer images while maintaining volume. The use of determinant can also help to evaluate the uniqueness of solutions and provide important information about possible instability or failure in structural stability analysis. To summarize, determinants are an important mathematical concept with a wide range of applications in analysis and problem solving. Thank you.